everybody. Thank you so much for joining us today. We are so excited to dive into how you can do physics at the amusement park. This has been such a fun webinar to work on, so we are looking forward to diving into the science here in just a little bit. As people get settled in, I just want to introduce you to the way we run our webinars in case this is your first time here. Go ahead and navigate to the bottom of your Zoom window. At the bottom of the Zoom window, you'll see what looks like a little chat bubble. If you click that chat bubble, you'll be able to bring up the webinar chat, and that's how we'll ask questions, etc. during today's webinar. So make sure you put your questions in there. If you click that chat bubble and it pulls it up, you'll see at the bottom two and then a little blue button. Right now it might say hosts and panelists. Go ahead and click that button and set it to everyone. That makes sure that everyone can see your chats. We particularly appreciate you sending your questions to everyone because that way, one, we can all share in wondering something, not knowing something, and two, we won't look like we're talking to ourselves when we answer your question. So as you submit questions to the team, please make sure your two is set to everyone. That just helps us a lot and builds our community. To warm up what we've just learned together, go ahead and, as I said, navigate to the webinar chat and let me know in the chat. I'm going to pull up this poll in just a second. But in the chat, let me know what has been the highlight of your summer break so far. I know some people are getting ready to go back to school. I think a few folks are already back to school in some areas. So let me know, was it camping? Was it fireworks? What made it fun? I see Julia S. went kayaking. That's awesome. Jack R. visited the grandchildren. That's amazing. Steve went on a trip to the East Coast with his wife. Traveling to Washington State. Awesome, Jamie. Um, let's see. Visiting Italy. Okay, lovely. Bought a 3D printer. Very cool. We have a Thingiverse somewhere on the internet where you can find 3D printing stuff for Vernier if you are so inclined. Oh, Jonathan hit 2 amusement parks. So this is very timely for you, Jonathan. Josh took the kids cliff jumping in Utah. Very cool. All right. Let's see. So we're about 2 minutes past the hour. Let's hop into some housekeeping items really quickly. If we can go to the next slide. Beautiful. First and foremost, you will receive a recording of today's webinar. It typically takes us about 3 to 5 business days to get it edited and uploaded. But as soon as it's uploaded, it'll be both on our YouTube channel and our website. So keep an eye on there. We are also going to email a link to that YouTube video. So keep an eye on your inbox. It's coming your way. In that email, you will also receive a link to today's resources folder. We've got a certificate of attendance in there. We've also got today's presentation with clickable links, some experiment files, etc. So take a look at that as soon as I'm done talking. As I mentioned before, please drop any and all questions into the chat box. Just make sure you set it to everyone. And if we happen to not get to your question or you think of something later, email us at physics@vernier.com. All right, I now have a poll, just a fun poll to pull up for you all. So you should see that on your computer screen. I
Yeah,
just
I
want
have
to
to
know,
see.
why teach physics with roller coasters? And there's no right answer here. So go ahead and choose what feels right to you. The answers I see rolling in are not a surprise to me. So
I can't vote. I can't.
that's awesome.
Bang.
And I'll just wait for folks to stop answering before I share the answers of the poll. Um, I'll say a lot of people are doing roller coaster physics because it is just fun, which, you know what, I get it. And I had a blast taking videos for this webinar. So big agree there. All right, I'm gonna go ahead and end it just so we can keep moving, but a fun thing to think about, and feel free to drop your answer in the chat if you didn't get a chance to vote. So I'm sharing the results.
50%.
I agree.
I will say I had kids take AP Physics just because they knew that we were gonna go to Six Flags at the end of the year. So some kids, the reward for sticking with the class.
Yep. All right. Well, I will hand you off to today's presenters. Please make sure you stay until the very end of today's webinar because we are giving away a sensor at the end of the presentation. So stay tuned and you might win.
Thanks, Dylan. So here in the studio at Vernier Studio, we have myself, Tom Smith, and Josh Ence. Unlike Josh, I never did take my classes to the amusement park. And I was really excited this summer when we decided to do this webinar and we were all going to go to the park and take videos. And then I broke my ankle so that the day that they went to the park, they went without me. So I'm shooting a little bit from the hip here, but Josh is here to keep me on the straight and narrow. And for the webinar today, we're going to be talking about using video analysis as well as graphical analysis, data collection with our GoDirect acceleration sensor. Here's kind of a brief agenda. The shared folder has a lot of resources in it. It has this slide deck that includes a lot of hyperlinks, so you might want to make sure you grab that. We're going to talk a little bit about some resources for planning your trip because you could certainly just take your physics class to the amusement park and have a great time. But if you want to have your students get the most out of it, some advanced planning is in order to be sure. We're going to talk a bit about the GoDirect acceleration sensor and remote logging, a relatively new feature for us here. We're excited about it. And then we're going to work through a couple of activities with a couple of the rides at the park, the tree top drop and the roller coaster. And we'll take a look at, what is the other one that you rode?
Atmosphere.
The atmosphere. It's kind of like a physical pendulum.
Yeah, overblown physical pendulum.
Yeah, so we'll take a look at that as well, and then spend some time talking about sensors in general that may be interesting phenomena. So Clarence Bakken is one of our consultants. And he was a physics teacher for years and years and did a lot of work taking his kids to amusement parks. And he wrote a book back probably, I don't know, the last publication date was, I think, 2012 or something like that. You can find his book at the AAPT bookstore. It has a wealth of information about how to get organized to go on the trip, as well as recommended activities to do at the park. So if you're brand new to this and haven't really thought about, okay, I need to start talking about this in the fall, so when we go in the spring, kids know what they're doing, to set yourself up for success so that your parent-teacher organization will be glad to rent you a bus for the day, et cetera, et cetera. Great resource. The other one that I stumbled across when I was preparing for this was Six Flags actually has a really good set of instructions and guide for both a teacher-oriented one and a student-oriented one. The lesson plans tend to be 3D kind of NGSS aligned to a certain degree. And they obviously focus on the rides you would find at a Six Flags park, but they are certainly universal in their intent. So easy to kind of modify those to fit your needs as well. Josh, do you have anything to add about getting prepared to go to the park?
The only thing I decided I would add, as far as our webinar goes, is we're going to kind of focus on the data collection and analysis today, because that's kind of like our jam. But like Tom mentioned, Clarence Bakken's book is really great for all the logistics, like all the little things that you might not have thought about beforehand, the permission slips and organizing groups and all that kind of stuff that it's important, especially if you really want to take your kids to an amusement park, but you may not have thought of before.
Yeah, I'd third that, or at least second it. So here we go. So we're gonna spend some time, and Dylan, I'll ask you at this point to grab those links and put them in the chat if you would. We're gonna use Video Analysis and Graphical Analysis Pro, and those links provide you access to the Pro version of graphical analysis and access to video analysis through the end of next week or the beginning of the following week, August 4th. So if you want to play around with the resources that we've put in the shared folder there, that's a great thing to pick up. And of course, you can get to those same links through this slide deck, which is also in that shared folder. And I'll go ahead and move forward, but those should be popping up in the chat here shortly. So talk a little bit about the GoDirect acceleration sensor. The latest version is a version that is remote capable. You'll notice this right here. Symbol will indicate whether a sensor is able to store data when it's disconnected from graphical analysis. And yeah, we'll demonstrate that here shortly, actually, just to give you an idea about how that works. The sensor has two different ranges for acceleration in 3 axes, X, Y, and Z acceleration. It has angular velocity, so it has a gyro built into it that can measure rotation rate. It has an altimeter in it that will give you an indication of altitude, as well as an angle indicator, which I don't think we used in the park, but certainly we used altitude and the accelerometers. I'm gonna exit full screen here for a second and take a quick dive into graphical analysis. And we have here, we're just gonna take our, I'll hold this up to the camera so you can see the small, very small accelerometer. I'm gonna turn the power button on and we'll hit the sensor data collection button. And there it is. Make sure we connect to the right sensor because it'll start flashing green there. It does. I'll note that you can access all the channels here. For the park, we use the altitude quite a bit. We use the gyro, we use the accelerometer. I'm just gonna show this with the X-axis acceleration just to demonstrate remote logging and how you access that. So I'll click done there. Maybe I'll boost up my view here a little bit so you can see that. And then in the data collection settings, so where it says mode and time-based down here, this is where you can enable remote logging. Now let's click on that there. Right now it's set for manual starting of data collection and gonna continue collecting data for 60 seconds. I'm gonna start on a triggering event. And I'll just arbitrarily say when the acceleration is increasing above 5 meters per second squared, and we'll decrease this so you don't have to watch a minute's worth of data collection here. So when I click done, now instead of saying collect up here, it says start logging. So I'll just hit the start logging button. Josh, you want to talk a little bit about the
Sure.
LEDs there?
So when you start logging, the sensor disconnects itself from graphical analysis, and at this point, it's waiting for the trigger value to be met before it starts collecting data. So like you won't be able to see it very well on the screen here, but right now the little LED is flashing red and green, meaning it's just waiting, sitting and waiting. Once we, oh, I triggered it. Once I triggered it, it's collecting data now. Now it's double flashing green. And in about a few more seconds here, now it's double flashing orange, means that it's collected its data, it's stored on here, and you're ready to retrieve that data.
So in order to retrieve the data, we have to reconnect to the sensor. So we come back over here to the little the temperature probe that Josh likes to call a spatula, and we find our accelerometer and we connect it to it again. You'll notice that this dialog is different than what you've seen before. It'll say you want to retrieve and clear the sensor because it recognizes there was the data stored on it. You could disconnect without doing anything, just saying, okay, I know it has data on it. I don't want to connect to it right now.
You might use that one if you have multiple devices, multiple computers at the park, and kids are downloading their data and they inadvertently connect to the wrong sensor. You're like, oh, actually, I want to connect this to the other. They might just disconnect without clearing any data.
You can also just clear the log data, but we're going to retrieve and clear the data right here. And there are the data. You'll see that
Very exciting.
Josh did something exciting here that just triggered 5 meters per second squared on the accelerometer, and then kind of held it wiggly for a little while. So there it is. That's it's ready to set up another data collection event, but we're gonna move back to the slide deck for just a moment, I think. Yeah, so let me go back to the slideshow. There we go. So I want to talk briefly about Graphical Analysis Pro and what we're going to show you with that versus what video analysis does for you. So with Graphical Analysis Pro, just like I showed you, you can do remote logging. You can also take video and synchronize the video to the data that you've collected. You just need to be a little bit conscious or clever about your video. Make sure you have some means of figuring out when the video should be synced up with the data, which is not too bad to do. And then you have video that you can watch stream at the same time that your data are being played back. It's a really nice feature. We'll demonstrate that a few times today. Contrasting that with video analysis allows you to import a video and then use a tracking device, a tracking tool, to basically mark the motion and convert that motion into data, into position versus time data, which then you can calculate velocity versus time data as well. So it doesn't involve data collection from a sensor. It's just data that you've been able to capture from the video itself. And just to make that distinction clear, one more way is in Graphical Analysis Pro, you don't have the option of marking that data in the video. It's just the sensor data that you're collecting data with. Okay. Practice before you go. Yeah. So did you guys do this before you went?
We did actually, yeah. So when we went to the park, we went to the Oaks Amusement Park a couple of weeks ago. That's kind of our small little amusement park here in Southeast Portland. And we set it up and just practiced first with the Go Direct acceleration sensor. We want to make sure we understood the process, and especially like we had put a lot of thought into, well, what are we going to trigger off of? You know, we think about a particular ride. What can we do so that it triggers at the right time and not while I'm just standing in line or whatever, you know? So we practiced just connecting to it, understanding what the little flashing LEDs meant, that sort of thing. As we were at the park, I felt like if we were to do this with students, it probably would be good to have a couple of laptops, 2 or 3 laptops, and have kids go out and collect data and then come back to a laptop and download it right then and there. That way it's saved. Ideally you have you're saving to, say, the same Google Drive or something like that, and you have some sort of naming convention for who took the data and when they took it and what ride it was, sort of thing, so that later when you get back to school, you have you can sort through these files easily. The other thing that we thought a lot about as we were kind of setting up was, like, what orientation are we going to hold the sensor in? You can take, X, Y, and Z acceleration data and do the square root of the sum of the squares and get a kind of an overall acceleration. But if you want to kind of tease out direction, it's good to know what orientation the sensor is going to be held in. And there are a couple of ways to do that. Fran, you can see Fran here, she used one of these phone cases, like you're going to go for a run, you want to stick your phone or your iPod, I don't know, do people still use iPods? iPod in there, and run with it, sort of thing. But even then, this go direct acceleration, it's about the size of like a tube of chapstick, so it's relatively small. And even something for a phone, it's a little big, and so it might slide around while it's in there. So Fran fashioned a little plate to attach it to. Go direct acceleration comes with a couple of different brackets that you can use to attach it to things. Say you want to use it on a shake table. This makes it easy to attach it to the shake table. Or if you want to attach it to your bicycle or something like that, there are a couple of different brackets. She attached it to a piece of cardboard and a piece of balsa wood so that we could hold it, so it would be held in an orientation. And then this piece of balsa wood is the right size for the phone holder. And that way she had it on her arm. She knew that the positive X direction was pointing up towards the sky, and that helped her. Well, it's helped us interpret the data afterwards. I was not as prepared as Fran, so I just stuck it in my pocket. And for many rides, that works out fine. If you can it's like it's sitting on your lap, and you can have it so the positive X direction is pointing, towards your knees. And in that case, in most play cases, that was totally fine. The only place where I really felt a little uncertain about that was the ride that Fran is in this picture here with Fran, the atmosphere. It's like this big swinging physical pendulum thing, and you go upside down. I was just like, for that one, I wish I had had a more secure way to hold my my go direct acceleration. So maybe do you want to stop sharing for a moment, and I'll kind of, just so you can kind of see what a little bit more how the oriented it here. So you'll see with go direct acceleration, maybe I need to get closer. Oh, maybe there are axes drawn in. The x-axis is along this way, So if you collect data, you want to come back and look at it. It's good to know, like, what was X? What was Y again? X is along this length. This is actually positive. That means that Y points this way and Z kind of points this way. When Fran had this on her arm, X was, because of the way that this phone case fits, X was pointed towards the sky, and kind of like the positive Z direction was forward. That's good to know when you want to interpret your data later. Yeah. Is there anything else we want to do about? Oh, I guess the other thing you want to do is before you ride any ride, just kind of scope things out as far as, like, what can we take good video with, and where can we take that video? We were lucky that at the Oaks Amusement Park, there were a couple of rides where you could get far enough away that you could get this nice view of the ride moving up and throughout all of its motion. You'll see we took some video of the loop in the roller coaster. That also, you had there was just a wonderful place you could record video from. Some rides are going to be easier than others, and that might affect, what kind of data you ask your students to collect, or what kind of data they want to collect, and that sort of thing.
Make sure that you pack a meter stick or a flexible ruler of something that you can measure something in your video. That's something I always forget when I go to take video for video analysis, is to have that scale built in there. We'll talk about a couple of things that we that they stumbled across in their trip to the park. We'll go back to the slide deck here. You talked a little bit about triggering.
Yeah. Yeah, we triggered a lot off of altitude just because, we knew that a ride was gonna, like on a roller coaster, you climb up the first hill sort of thing. And so that seems like a natural way. If I'm here on the ground level, I know that I'm not easily gonna exceed 5 meters if I'm not on the ride. Um, you can also trigger off of acceleration, but that requires that you know some sort of acceleration, like what would be a typical one. So that might be a little bit harder for your students. We found that one way to trigger off of acceleration was the whack it method, where you would just like say trigger off of the x-axis, and I'm going to set it to say 30 meters per second, which is kind of a large acceleration, but it's large and it's large and it's just not going to happen on its own. But it's not so large that you can't just whack it with your hand or something like that to get it started. So we'd often do that is we'd get on a ride and then you'd whack it just before the ride began, and that would start the data collection.
Some good tips there for
Yeah.
getting started.
Rick is asking about the resolution on the altimeter. We're going to show you some altimeter data here in a few minutes, Rick. You'll see that it's pretty coarse as far as or on the order of about a meter. And so if you were just taking, you'll see it looks pretty fuzzy. It's good enough for what we need, but it looks pretty fuzzy. If you're taking this up the side of a mountain, it looks much better just because the resolution is so much smaller.
Okay, I wanted to, this is
I guess there's one more question here. Todd asked
yeah.
about if you could set up multiple ride files and then simply load the specific ride file onto the probe before the students go on that ride. You could. Definitely you could say, like, I know I'm going to go on this roller coaster. I know the roller coaster is it takes 60 seconds, a 60-second ride, and I know I want to trigger off of the altitude. And so I'm going to say when it passes 5 meters or something like that, and set that up as a template file. And then when you get to the amusement park, load that template file, connect the probe. I guess you'd want to connect the probe and load the template file, and then hit start logging. You could definitely do that. You might, part of me says you might not want to do that simply because there's good teaching moments in there, asking students to figure out like, what should we trigger off of? How long should I collect data? And if that means that they have to stand and watch the ride for a minute and use a stopwatch on their phone to figure out how long the ride is before they actually, I think those kinds of questions are good, and those kinds of exercises and thinking about what the data collection parameters should be are a good exercise. Obviously, for some students, some classes, it'd be good for you to say, this is what you want, let's set it up. In other classes, especially like your AP classes where you want students thinking about the experimental method and that sort of thing, having them go through the step of choosing the data collection parameters themselves would be a great, exercise.
Great question. Yeah.
Yeah.
So I'm going to show you a video of the treetop giraffe. I can say that.
This is let's be honest, this is a little kid ride, but it had a great place you could film from, and it actually was pretty fun.
Good physics involved.
Yeah, great physics too.
So you can see wiggling feet there, some by Vernier employees, some not. So, even if you weren't able to go to a park, but if you had a video of an event like this, you could challenge your students to think in advance, well, what would an acceleration versus time graph look like for this? What's going on that would show up in the data? You notice there's a couple things going on. You're rotating, you have a little angular velocity there, and you're also going up and down, being accelerated in a variety of directions there. So, and then everybody's relieved to, what is there, that a 30-second ride or something like that? A lot of people get to view that. So we're gonna take a look at data that was collected on that ride. Let me just pull that up real quick. Went the wrong direction, so I went to open. Not save that. And we're looking at this set of data right here. This is actually the angular velocity data. We can take a peek at that for a second. You'll notice that there was, it's probably Josh standing up and turning.
Oh, getting off the ride,
like
yeah.
Yeah. But, you know, this section of data right here, there's a portion of this that is pretty constant angular velocity. So that might be something to kind of explore a little bit what's going on there. But what I was more interested in taking a look at, if I can, is the, so we have altitude data. Let's take a look at that for a second. So, you know, you're climbing up, triggered off of some event of a certain altitude, I assume. And then you're going up and down and up and down. At the top, you stop for a few seconds and then slowly decline. So we pretty much saw that there. I was surprised when I looked at this alongside the acceleration data. Without thinking about it too strongly or too deeply, I was expecting peaks to line up. And when they didn't, I had to stop and think real carefully about, well, what actually is going on? How is it that I wasn't at the peak altitude when I was that peak acceleration occurred after the peak altitude? So there's some good sleuthing to be had there. It might be useful to think about, what's going on in the video at this point and sync that up. So I'll show you how to do this, and then I'll just jump to a version that's already set up. So you can go to video and import video. And then we can take that same treetop drop video and open it up here. And it shows up here and you can play the video. In order to sync it, you need to have some timestamp in the video that corresponds to something of note here. And what I tried to do initially was just to go to this where it's basically resting before it starts to come down, and found that spot here in the video. And then when I got that time for that from the video, and along with the time here in the data, then I went back up to, thank you, enable replay, and go to this little sync video button. And that allowed me to set those two timestamps together to synchronize that. Rather than watch me do that now, I'm just going to open up a version of this where that's already done. So let me not save that and go with the video. Go.
This synchronizing the video with the data collection is one of the Graphical Analysis Pro features. So Tom shared that link earlier in the presentation. So if you want to try this out yourself, you'll need to activate Graphical Analysis Pro.
So I'm in the replay mode here, and you can see I've sped this up to 2 times. This would be a really fun ride if we were actually going that fast. But it just to illustrate that connection between the video and the data. I will note that this turned out to be a pretty valuable data point here. This is where it first makes a little jog and starts to drop down. And that was easy to pick up in the video as well as in the data. So you're going to have to look for something that's really distinctive to make that work.
One thing that you'll notice, those of you that are paying attention here or can see the screen especially well, is that the z-axis acceleration, so in this case, the accelerometer is kind of basically sitting in my lap, and z-axis acceleration is the up and down acceleration. That when you're just kind of standing still, the z-axis acceleration measures about 9.8 meters per second per second. And that can be a little confusing. We usually think of acceleration as, the rate of change of velocity. And if I'm sitting here and I'm not moving, my velocity isn't changing, why would my acceleration read positive 10? And the reason is this, even though we call it an accelerometer, isn't really measuring acceleration. What it's measuring is the normal force per kilogram that it's applying to the little bit of mass on the end of a little cantilevered finger. It's, as that cantilevered mass moves up and down with the motion of the accelerometer, the voltage read across that cantilevered arm changes, and that voltage is then are essentially calibrated to our acceleration. But it's really measuring normal force there. So when I'm standing still, there is a normal force pushing up on me, all right? And that's why you get a reading of 10 there. Side-to-side accelerations make more sense because, it's not moving, and so the acceleration that it measures and a side-to-side acceleration, that you understand. But it's a little bit different when you have an object if you're oriented in such a way like this, where you're moving up and down, that acceleration is going to read positive 10 when it's pointing up and you're at rest. Obviously it changes as it goes through there, but that kind of tells you your baseline.
Okay, I think we're going to move on to the next ride here. And that is the roller coaster, the Adrenaline Peak at Oaks Park. And looking at a couple of things, I built this and then I didn't follow up with it. So we look at the loop-to-loop acceleration and the motion through that. I think there's an opportunity to play around with conservation of energy as well, but we didn't do that yet. So we'll leave a little bit for the audience to fill in there. There is a link here I'll point out. Let me just make that back into the slideshow for a brief moment. How to collect good videos for analysis and video analysis. So this is a resource on our website that is just a great set of tips on how to set yourself up for success in taking good video. Of course, being outside is one of the tips, and at an amusement park, you can't help but be outside. So. Let's see. Okay, we'll go back to graphical analysis here to start with.
We have maybe before we have one question in chat. What happens if you drop this? What if it's in free fall? What does it measure? Do you want to do it real quick? We can connect.
Sure.
Yeah. It's a great question, William. We're going to connect to this, and you'll see it with your very eyes. So we're just going to collect, and I will do my best to put this in free fall for a good amount of time.
So it's
I've got 60 seconds.
Yeah, let me get
get
all three channels.
Get all three channels. Yeah. We'll turn on X, Y, and Z acceleration.
And then
maybe set the data collection time just 10 seconds so you don't have to stop.
Yeah,
you could.
That's a good idea.
I guess you could stop.
Still might stop at paint.
All right, so right now I have it oriented face up, so positive Z is pointing up. Let it sit for a second, then I'm gonna toss it.
Oh, that's good.
Okay, yeah, and then I'll toss it again. All right.
So you can see everything, all three axes basically read 0 when it's in free fall.
Yeah, so that's why if you're thinking about this as acceleration, that might also be confusing. Why isn't it 9.8 meters per second downward, right? Well, there's no normal force, so that's 0, right? That does also help you understand, like, if I want to know when this is in free fall, I should look for when the net acceleration reads 0.
Great. Okay, so let's go.
Yeah.
Sorry
You want
to
to go to video analysis now? Oh, we'll look at the roller
we'll
coaster.
look at the roller coaster data first, and then we'll go to video analysis. Yeah.
Okay, yeah.
So let's see. We'll just get the data up here. Go ahead and make that full screen so we can see it. On the X, Y, and Z axis, we have our acceleration here for the roller coaster, and then we have the altitude. I assume, well, I don't know what we triggered off of.
Actually, you can tell if you look carefully, you'll see that time zero is actually at the altitude of about 5 meters. That's because that's what we were triggering off of. But we did set it so that it would collect data before the trigger. So it's like it's always collecting data, it's waiting for the trigger, and then it just saves I think we set it to like 100 points before the trigger. So that's why you can see it. It seems as if you collected data at negative time. And that's just because it saves some of that data before before you did your Mark asks about zeroing the sensor before. You can zero it before you do remote data collection. Usually the way it is you connect to it in graphical analysis, you zero it, and then you set up the data collection, and then you hit start logging, and that's kind of where.
Yeah, the risk of that though is that you're zeroing one axis of I mean, typically it would be oriented flat, and that may not be the way you're going through the ride. So that you're
if you had it on, let's say in you had it attached to your arm, you'd have to be sure that you're zeroing what you want to zero, Rick asked about pre-triggered data, like how much would you want to save? And that's kind of it just kind of depends on the ride. In this one, we know that for this roller coaster, it's like a typical roller coaster where you're like chink 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 climbing your way up the up that first hill before the loop. And we wanted to capture enough of the data before the trigger that you could see kind of like that full run. But if we had messed it up a little bit and hadn't captured enough, you probably still could interpret the data. But usually what you're looking for is, that it kind of depends on the trigger you choose. If you choose a good trigger, you might not need to collect any data before the trigger. In other cases, it's not. In this case with the roller coaster, I didn't want it. You could have used the whack method and had it, and then you wouldn't have to worry. But this one we were still kind of feeling things out.
So one of the things, if you're wearing this on your arm or something like that, you want to make sure that your kids know not to raise their arms as they're going through the roller coaster. So it's going to mess up their data in a different way.
You don't want to mess up the data.
Yeah.
Not for the sake of fun. No.
That's right. So we see here, like I'm looking at the data up here. We're obviously climbing up the incline. We're basically looking at kind of just not accelerating at all, just having a kind of a constant value of that normal force again. And then once we get up here where we're just about going to drop off, actually, this is a really nice one to use, even though we don't have a video with this right now, to just watch the replay. As you can see
this roller coaster has a really pretty much vertical drop once you pass over the top of the hill.
And there it is.
Yeah. And then it goes straight into a loop, and then it does a whole bunch of turns and flying around. I don't think it goes upside down except for the one time during the loop. It's a great little roller coaster though.
Yeah. So I'll just stop that there. And I think I will go to video analysis now to take a look at that. So let me minimize that. Go to video analysis. And I'm going to do a couple of things here. First thing I'm going to do is just import. We have two videos. One is a video of somebody going through the loop here. So we set this up, we can just watch this happen. If you assume a roller coaster is a fairly repeatable experiment, it doesn't matter whether this is your group or not. but you can just take a video of it and capture that information. You're really only interested in the part where the cart shows up, right? So somewhere in here, even further, further. There it is. You know, you're halfway through the video before you have anything of interest. So if you can, I mean, to make the experience a little more useful, you can actually trim the video either on your phone before you send it to yourself, or whatever you're taking the video with. I just went ahead and I trimmed it with a tool that you can get online. I think I used B-Cut as the tool for this round, but there's a Cloud Convert or a number of different video editing tools that are free or relatively easy to use. And it just allowed me to shorten that up. The nice thing about that is that the video takes up less data, so that it's easier to port over to other
Small
platforms. I will briefly show you kind of the steps for doing the video analysis, and then I'll just open up an item here. So in order to set the scale, we need to know the height of something. I'll kind of get here to a certain point, and then I'm going to zoom in.
Yeah, we measured the height of the fence, this fence post right there. Yeah.
This post right there.
This
one in the back.
Yep. There's a fence immediately, like kind of separating you from the roller coaster, and the tall fence posts were 1.8 meters tall, or 8.6, I think, meters tall.
So there, that says the scale. We can put the origin pretty much anywhere we want to. Thought it might make sense to maybe get the cart on here. Let's see if we can capture that.
Right.
Now, you might think about this. I'll get this out of the way for the moment. I'm going to mark this person's head. That's about the brightest thing that I can see as the origin. And that's what I'm going to mark as they're going around the loop-to-loop as well. But you might consider like class fluorescent green t-shirts or something like that, or a beanie that's bright orange or something, so that it's easy to pick up the person moving through the video as you're doing the data collection. And then to actually collect data, we just mark and mark again and mark again until we get all the way around the loop. You can speed this up a little bit. You could mark every 2 frames or 5 frames, just for the sake of showing you a few more data points. And then rather than just completely putting you guys to sleep that are watching this, I'm going to go ahead and open up a already tracked version. So must be it. And there we have the data. We can just show the graph and the video. We have a line of best fit here for a linear fit. For what we're looking at here is X velocity versus Y velocity. You could look at the X position and Y position as well. But we're kind of interested in what was happening kind of in this range, where the cart is just going across the top of the loop, and then looking at the Y velocity through there as well. Might be worth just going through the replay once to kind of watch that data come in. Yeah,
it is pretty interesting. If you click in the graph, it shows you the frame where that was collected. So I'm going to actually, so I can see all of it at once. So like this is, you can see we're starting the loop here. And then over here, we're kind of getting to the other end of the loop. And during that time frame, it's interesting because we have velocity graphs that look very much like projectile motion.
Mhm.
The X velocity is fairly constant. It's negative because we're moving to the left here rather than to the right. And the Y velocity starts out positive and large, decreases to 0, and then gets larger in the negative direction. And so it's almost like the roller coaster. You could imagine the roller coaster throwing you up into the air, and like you were a projectile, and then catching you on the other side. I think that's kind of cool because, as it's likely that in that, the second month of school, you're teaching students about projectile motion and what projectile motion looks like and how we characterize projectile motion. And then at the end of the school year, they could go ride a roller coaster and collect a video like this and say, hey, for part of that ride, it's like you're a projectile. You just get thrown into the air.
And looking at the slope of the line, you can tell that you're not actually in free fall. There's a little bit of contact with the rail, but for a large part, you really feel like you're flying up there. So it's pretty cool. Great. And you could certainly sync a portion of the data that we took with Fran's accelerometer with this portion of the video and take a look at the motion that's going on there with the acceleration as well.
You might have some groups collect acceleration data using the accelerometer, and other groups collect video and analyze it this way, and then come back together afterwards and talk about like, well, how did your data compare to my data?
Any other, we want to talk a little bit about good tips for taking video. Certainly having a scale, something recognizable in your video that you can measure and note that distance. That you want to have that as close to the plane of the motion that you're looking at, as well as having your camera perpendicular to that plane so that you're getting a good head-on view.
You can see the photo here is at more of kind of a 3/4 view of the loop, and so you could collect data, a video this way, and analyze it, but because your camera axis is not perpendicular to the plane of motion, you're going to end up with some like skew data, along those same lines. We were fortunate that when we went to the amusement park, it was a nice sunny, you can see it was a beautiful day. We had very good lighting. Usually when you film outside, you've got pretty good lighting, but if you were to compare this to a marble track that you made inside, you'd want to make sure that anything you film inside really has good lighting. The more lighting, the better, just because that's going to reduce more of the kind of like the motion blur that you see, and it'll make it easier to track.
Yeah, you do want to pay attention to shadow when you're out there, though. You can tell that in the video analysis that we just ran through, the cart was in shadow in some portions of the video, and it was a little harder to track through that. So. Okay, the physical pendulum. I do have video for this, so we'll have to watch and see what it's like. So let me go. Let's see. Atmosphere. There you are.
So basically it's a big pendulum that swings back and forth. But you kind of sit down there on the bottom, and it rotates while it's swinging. So sometimes you get a real great view of the sky. Sometimes you're looking straight down at the ground. They have actually 2 lines for this ride. One, it only swings 180 degrees. And then if you get in the other line, like this one right here, it actually goes all the way around 360 degrees. Yeah. It was quite a ride. Well, Fran and I sat in just the right spot that we get to that highest point and you'd be staring straight down at the pavement. That was a little nerve-wracking.
So I want to show you some data that they took from this, and just as an example of some interesting anomalies with data. So go to open and atmosphere. There we go. So pull up
This
the,
is angular velocity data, so it was turning the whole time, and you can see it did change direction that it was turning at midway through the ride, part of the way through the ride. When it gets going real high.
so the interesting data though is this right here, where it seems to imply that it never quite got back down to the bottom until the ride was over. They started over here, and then as they started to swing, it just never went down. And
Yeah, this would be a little confusing. If you were a student, you're expecting that this is swinging back through, you ground zero each time, each swing, but it looks like that ground zero is getting higher, rather than being where it started, it just starts creeping up and up and up. And this was a little confusing at first, but then we thought a little bit more about go direct acceleration and the altimeter. And the way it measures altitude is by air pressure. The idea being that when you're at higher altitude, there is less air pressure. And when you're swinging really fast, especially in the middle of the ride, you're moving quickly, and the apparent air pressure is lower because you're moving fast. That's like a Bernoulli's principle sort of thing. And so that means that the bottom, the bottom of each of these swings is higher than it really ought to have been. I thought that's interesting because we like to think, we're a company that sells digital probes and sensors to measure things, but you always got to remember, what is this thing actually measuring? If even though it tells you it's in meters per second, it might be easier sometimes to think of it as newtons per kilogram. And even though this measures the altitude in meters, it's mixing in a little bit of speed in there too. That's why you end up with these strange stray. You end up with a zero that seems to climb and then decrease.
it's just a really great opportunity though to talk about sensor technology and to help students build some context for, what actually is going on with this sensor, what do I need to be aware of when I'm creating an experiment on my own?
It's tempting for students to treat the black box, although this one is gray, to treat it as just, well, that's what the data is. It gave me, this is what said the value was. It's important that they understand how, not just what it's measuring, but how it's measuring it, because that'll help them then later to interpret their data.
Yeah. So I have another link in here that talks about what does our accelerometer actually measure, and I noticed in the Six Flags document that's linked in there as well, they actually talk about the air pressure and altitude
cool.
readings. So there's some good information in there about sensor readings, sensor data collection. Here are the products we talked about today, the Go Direct Acceleration, and there's a bundle for Graphical Analysis Pro and Video Analysis. You can buy them together. Just know that those links are there. And we'll pause for some questions.
I think we got all the ones that were in chat. Oh, Steve, Ethan suggests that you take a string marked in meters. That can be very helpful. Like if you don't want to bring a meter stick and you gotta need to measure like references, having just a string, that can be really helpful. I had this big old long tape measure that we would use also for water rockets and that sort of thing, but it wasn't the most, compact sort of thing. Todd Snyder asked, can you manually trigger start for remote data collection? And if so, why don't you use it? So the options are just start right now, or as soon as I disconnect, or start on a trigger. So the triggers that we chose typically were things like the altitude, or the other option was we'd set it to a relatively high acceleration and then just whack it. That was probably easier than trying to manually push a button or something like that. If you just whack it, that was the easiest way to get it to trigger, you know.
Yeah, but there's not a button that you can press on the sensor, for example, to manually trigger the start. So, well, thank you for all of you hanging in there with us. We've enjoyed the time together. And Dylan, you're on.
Yes. Amazing. So, as we have been in today's webinar, I entered everyone's names into a random name selector. And the winner today of a GoDirect acceleration sensor is Cody A. So, congratulations, Cody. I'm going to email you. Keep an eye out for an email from someone with an @Vernier domain in their email. And I just have some shipping info to get from you. So, congratulations and thank you so much for joining us today.
Thank you everyone for being here.
Yep.
It is taking your students to the amusement park is really a great experience. It's gonna be lots of fun and it can be very educational.
Thanks again.
Have a great rest of your day, everyone. Thank you. Bye now.